All right, so in example 4, we need a test to see if t plus v does equal. So t plus v this time, I would need to take my t's and add it to my v's. How do we add vectors one more time? All right, we add the x values and the y values, right? So I'm going to take my t, then my v. So in this case, this would be a negative 5 plus 3, and then 2 plus 7. All right, so all that happened was those numbers got flipped. However, when we add them up, what is negative 5 plus 3? Negative 2. And what's 2 plus 7? 9. Good. So did we end up getting the same answer as v plus t? Yes. Why? What do we know about addition? It's commutative. Order of addition doesn't matter, right? So if we're independently adding the x and y values, that means when we add vectors, they'll end up being the same result. But let's show that they end up equaling the same thing graphically. So in the first set on part B, we first graphed V and then we graphed T from the tip of V. This time we're going to start with T and then graph V from the tip of T. So here we go. So T was was negative 5 comma 2. So that's 1, 2, 3, 4, 5 comma 2. So here is vector T. So a little bit different because again, V went this way first. Now from the tip of T, we're going to graph V. So that means I'm going to go right 3. So that's 1, 2, 3. And then I'm going to go up 7. So that's 1, 2, 3, 4, 5, 6, 7. So again, 1, 2, 3, up 7. Give or take. This would be my V. So that means that this right here would be my T plus V. But what happens to be this coordinate right here? Negative 2 comma 9. Yep. So this time the only difference from part B is this time we started with T, then went V. The other one we started with V, then went T, but we can see they both ended up in the exact same spot. So graphically and algebraically, we now know that addition of vectors is commutative. The order will not matter. Any questions on that? All right. So I know we've done this before. It's a great little review. All right. It does. It does. Which is how we get magnitude for our distance. All right. In part 5, explain why, again, vector addition is commutative. What in y'all's own words? Addition. Um, addition of numbers. I like it. X1 plus X2 would equal X2 plus X1. Whatever your X values would be. And then you can also add in there too, like Y1 plus Y2 would still equal Y2 plus Y1. So even though we're adding vectors within the vectors, we're still just adding regular numbers. All right, in part 6, given V and T, which I believe are the exact same ones we've been having, we want to show numerically that the magnitude of V, sorry, I said magnitude, but these double brackets right here of absolute values means magnitude. Magnitude means not quite distance. You are thinking determinant. So be good. So find the area one more time is the square root of a squared plus b squared. Make sure you have those down as a formula. So what I need to do first is I need to figure out what is the magnitude of b. So I'm going to do the square root of 3 squared plus 7 squared. What is 3 squared? What? 9. Good. 7 squared? 49. 49 plus 9. Go ahead. Oh, okay, 58. Don't worry about writing it. Oh, wait. If again, don't stress about the fact that you have to find a decimal. You can keep it like that. You can compare radicands just as easily as decimals. So I'm going to keep it as square root of 58 and just kind of stop there. Now let's do the magnitude of t. So that's going to be -5 squared. Why did I put the -5 in parentheses? So it doesn't stay negative. If you are calculator dependent, you want to make sure you put parentheses in the calculator as well, because if not, you'll get a negative number inside. And you cannot have a negative number when you are squaring something. It's always going to be positive. So always put parentheses there if you like to plug it into the calculator. Again, this would be, I don't know why I put parentheses around that one, but this would have been 2 squared. So what is -5 squared? Positive 25. Very good. And then 2 squared. Okay. That would give me 25 plus 4, which is 29. All right, so we have this right here. Gives us 29 and 58. So now what we need to do is figure out what the square root of v plus t is. We're going to compare those. What was the answer to v plus t? Let me write a note up here. V plus t equaled what again? Something. Thank you. -2, 9. So I'm going to take these numbers as my a squared and b squared. So this gives me the -2 squared plus the 9 squared. -2 squared is 4. 9 squared is 81. 4 plus 81 is 85. So is the square root of 85 going to equal the square root of 58 plus the square root of 29? It might. All right. I want to get my handy dandy calculator real quick. A little 4 function calculator. Now I'm just going to do 58 square root of that plus 29 square root of that. And I get about 13. All right, so I'll come over here and I get 13 point blah, blah, blah. Now I'm just going to come over here and I'm now just going to do 80. That's a 5. 85. Do square root of that. Is that the same answer? So this basically came out to 9 point something equals 13 point something. So was that the same thing? No, they are not the same thing. So therefore, well, think of it like this. I love how you said this. So these are not the same thing. So part B then goes into it geometrically. So does everyone got part A down? So I'm about to erase it so y'all can see. Okay. So I love that because hypothetically in your head, you're like, well, if we add vectors and that order doesn't matter, then I should be able to add them and it should still be the same thing if I just add them first, then take the square root, right? However, if we look at it geometrically, this is going to be a rough sketch, but you'll get the idea. Let's take that last one we got. Right? This was like t, this was v plus t, right? What does magnitude mean? The distance, right? So the magnitude of t would be the distance of this side of the triangle. Magnitude of v would be the distance of this triangle. And then the magnitude of v plus t would be the distance of this triangle. When we first learned about triangles in geometry, hopefully y'all got to that point, can these two sides equal the hypotenuse? No. Right. You would actually have, you would have a line on top of a line and no triangle. So what y'all learned is side A plus side B has to be greater than side C to be a triangle. So then it makes sense that the magnitude of this has to be greater than the magnitude of A plus B combined. That make a little bit more sense? So if magnitude means distance, if I take this plus this, it has to be greater than that v plus t in itself. So this is why the magnitude of v plus the magnitude of t does not equal the magnitude if I was to just add them first before taking the magnitude. Okay? So don't make that mistake when you're asked to find it and you're like, well, I'll just add it first and then just move on with my life. Make sure what the question's asking. Okay? If you're asked for this, you cannot use this. And vice versa. If you're asked for this, you can't just go to this. Okay? Yeah, I might say, hey, find the magnitude of I might say find the magnitude of V plus the magnitude of T, right? I might ask this question. You don't want to add the V plus T first, then find the magnitude. You want to do them separately and then add them. Yeah. Any other questions there? It's a good question, though. All right, so part C, can you think of an example when this statement would be true? I heard it. If you had zeros, right? If you basically had two lines in a sense, but basically if you just had zero, right? Because if I take the vector 0, 0, and I call this, I don't know, V, and then I have T, and I call it 0, 0, what is the magnitude of V? 0. What would the magnitude of T be? And if I was to say, hey, what's V plus T, what would you get? Zeros. And then what is the magnitude of V plus T? 0, right? So if you happen to have two vectors that are just at 0, 0, then yes, this case would happen, but you also wouldn't have a triangle, right? You would just have a singular dot, right? You mean like, what if the X is 0 and or the Y is 0? Okay, let's think about that. Let's take 0 and 1, right? So that would be 0 squared plus 1. Let's just write it out. Let's say I want 0, and we'll do 2, right? And then my other vector will be like 3 comma 0. So something like this. Okay, so if we graph this out, 0 comma 2, so that'd be 1, 2. So here's my first vector, maybe a different color. Here's my first vector. And then from this tip, I'm now going to graph 3, 0. So that's going to be 1, 2, 3. So then I go there. So if I want that V plus T, here is what that answer would be. So would this link be the same as those two sides added up? Just geometrically looking. No, because then it wouldn't be a triangle again. Okay, okay. I like it. I like it. I like it. Ooh, that would work because what kind of shape would you produce? You would just produce a line. So if you did 0, 2 and 0, 3, so here's another example y'all could have used as well. But if I would have gone to 2, here's my first vector, and then from that tip, I then went up 3 more. Now I have another tip. So the combined total would be a line, right? So if I was able to do something like that, so yeah, so a second example would be if both of the x's were 0, or vice versa. If you had two vectors where both the y's were 0, that would also work because it would give you a straight line. But then again, not a triangle. But yeah, good, good. So those are three different examples y'all could have used there. Any other? All right. So let's work into example 7. It says, why is the vector, I think that's an O. Maybe it's a 0, but I think it's supposed to be lowercase o. Let's say call it 0, 0, called the 0 vector. Describe geometrically effect when added to another vector. So why would they call this the 0 vector? And that's it right there. So where's my pin there? Because when you add 0, 0, nothing changes to the other vector. That's perfect. That's why it's called the 0 factor, because anytime we used to add 0 to anything, it didn't change either. For addition, additive identity, yes, you can call it that. Because remember with the matrices, when we had the 0 matrix, that was the identity for adding. Any other good questions? That's perfect. Ooh, no, because you're getting into what we call dot products. And believe it or not, when you multiply two vectors together, you'll end up with a dot. We'll get to that at the end of this chapter. Yeah. Again, that's kind of where my pre-cal's heading, my online pre-cal. So I'll get to that soon. So adding two vectors gives you a bigger vector. When you multiply two, and we'll graphically show you as well. But when you multiply two vectors, you just get back to a dot. So typically, when we deal with multiplication, we multiply by scalar multiplication. So we take a number on the outside of the vector and then just distribute it in. So we can double the vector, or yes, so we can just expand it. Yeah, rotating would be like when I apply like trig functions, or let's say I have a unit here and I want to rotate it here or something like that, I would have to add another vector to make it like this, to make this new vector like this. Correct. Well, you can multiply it, but you get a number, not another vector. We'll talk about dot products when we get to it. It's not hard, complicated math. It's super easy. It's just a new concept to y'all. Oh, I know, I know. It has it moves the thing over, but when you multiply it, you end up with something different. What we've seen that in the past in math too, right? You take two complex numbers and you multiply them, what do you get? A real number, right? So that's why we played with complex numbers, because we could keep going. Because I gives you a -1. Perfect. So that's why we do that, and you'll see that happens quite a bit in math. When you take two normal things, you get like a whole new thing. You ever play that one game on your phone called Alchemist or something like that? I think it's what it's called, or Alchemy or something like that, where you mix like things together to see if you can make a new object or something. Yeah, it's kind of what math is. We took like two of the same things, or hey, this made something new. So that's what some mathematician was like, man, every time we do this, this is what produces or something like that. So they came out with some stuff. I don't know. Math was different back then because they didn't have technology. All right, so part A, or example 8. It says, given these vectors, it lists a whole bunch of them. It wants you to draw each vector with its initial point located at 0, 0. The vector V is already shown. How are all these vectors related? So I'm going to give you a moment, a couple minutes. Go ahead and graph U through R. V has already been graphed for you. All right, are we about ready? All right, so here we go. So if we graph U, that would be 9, 18. So that'd be about right here. So I'll do this in a different color. So that means this whole thing will pretend it is. All right, and then it says then the graph -3, -6. Hence your sarcasm, guys. There's 1, 2. I guess I should have labeled that. So this is S. This would have been was it W? And then this was U. And then we also have a T, -1.5, -3. So about right here. Nice straight line right there. We'll call that T. 612. We'll call that R. All right. So again, if you're a perfect artist, what did you notice about all of these? They basically all fail on a straight line. So there you go. They all fail. It's not F-E-L-L. Yeah, fail on the same line. All right, so that's what we can see graphically. Let's talk about this algebraically, right? So if I have V, which was 3, 6, what could you say about V to W? Go ahead. Or let's say V and R. So if V is 3, 6, what can you say about R, which is 6, 12? It's doubled, right? What can you say from V to U? Tripled. What can you say about V and W? They're just the opposite of their number. So you would multiply by -1. What would you say then about U and S? Not half, but not nines. A third. It ends up being a third of it. So you would multiply by what number? A third, 1/3, right? What would you also say then from V to T? Not a third. -1/2. So all of these other vectors, you could have gone back to V and multiplied it by another number. So all of these are, so all are scalars of V. Now you could make an argument that all of them are scalars of each other. Like you could say, well, they're all scalars of R, they're all scalars of W. I'm just going to stick with V since that was the first thing graphed. But they are all scalars of V. I can take V and multiply it by all those numbers. Go ahead. You can't get to W. W is tripled. You have to multiply. So that's why they're all scalars of V. So if I take V and I multiply it by a scalar, I can get the other outcome. So I can take V, multiply it by 3. I now have W. I can take V, I can multiply it by 2. I now have R. I can take V, multiply by -1. I now have W. Yep. U. Sorry. I got what I was saying. Well, it's a scalar of it. So remember, vectors don't keep on going. Right, but that arrow doesn't indicate that it infinitely goes. That arrow actually indicates that it goes from this dot to this dot. So remember, magnitude or vectors give you two things. Vector gives you magnitude, which is distance, and direction. So direction, and what we saw at the beginning of this lecture, I think, direction can be this point shifted north, then east. It went in that direction. It didn't infinitely keep moving, right? The earthquake doesn't keep moving the building. So I know that question hasn't come up yet, but these arrows, I guess what when you learn in algebra 1 or something like that, arrows indicate that they infinitely keep on going. But technically these are line segments, but this arrow has to be drawn for that direction because notice this arrow here is drawn to show that the direction is going down. Oh, that probably would have been good. Yeah, so you're talking about something like this. And then we could say something like that or versus to tell us the direction. That's actually not a bad idea, but that's just not how it's denoted. Whoever came up with this first gets to decide how it's written. But that's not a bad idea either. Yeah. Well, we have that notation too when describing if something's parallel to something else too. So maybe that's the case. Maybe it was already taken. I don't know. But yes, but that's a good question. I'm glad you brought it up. It doesn't actually indicate infinite direction. It just indicates direction. Just which way did I go? Oh, you talking about if we start with V, there was a pattern? No, that just quinkadink. Right, that's what I'm saying. So yeah, so sit on that one, that was a coinkydink that Y happened to be double to V or X. It's just if I can make the other lines from a certain vector, then they're all the rest of them. I could have 1, 1, 1, 15 or something like that. There doesn't have to be a pattern between the X and the Y. There just has to be a pattern between one vector to the other vectors. Right? All right, so perfect. So part B then says which vector is 2V? Huh? That was R, I think. Yes. So 2V would equal R, right? And how do we know that? R was doubled of V, right? We saw that the numbers just doubled. So any questions on that? Bless you. So geometrically, that's kind of what they're analyzing, but algebraically, it's not too bad. All right, let's look at part C. Let's describe the remaining ones. And we kind of already talked about all of them. So let's see. Let's look at U. What would U be in terms of V? 3V. What would W be in terms of V? -1, yeah. So typically we'll just say negative V, but you could write -1. What would S be in terms of V? 1/3 of V, you're right. What would T be in terms of V? -1/2 V. That's a 2. And then the last one we already did was R. So any questions there? So if you're having issues like understanding this, if I was to take 1/3 of 3, 6 and then distribute that in, I would end up getting 1, 2, which is what S was. So that's how scalar multiplication works. You multiply it by a scalar, and then you basically multiply it to the X and the Y. We all good there? Makes sense? Clear as mud? Bless you. All right, part D, if vector P is equal to 3 square roots of 2, comma 6 square roots of 2, is it a scalar multiple of V? Yes or no? Yes, what would the scalar be? What is it? Good. So P would be the square root of 2 times V. So if you think about it, if V starts at 3 and 6, basically when looking at another scalar or vector, you just have to ask yourself, what same number can I multiply both to X and Y to get the new one? And looking at it, I can multiply them both by square root of 2. So here's my next question to you. Let's call it Q. 3 square roots of 3, comma 6 square roots of 3. So this is a 2 and this is a 3. Would this be a scalar? No. Why? Because the numbers that you have to multiply X and Y are different, right? So this would not be. So just kind of watch out for things like that. So that was a square root of 2 and a square root of 3. Since they were different, not a scalar. I saw it. No. That one day a new math teacher will have better handwriting. Huh? Sure. Make a square root of 5. Is 2 and 5 the same number? Is the square root of 2 and square root of 5 the same number? No. This was just made up. I just completely made this up. As long as those two numbers are, even if you wrote a 3 or a 5, you should see that they're still not the same thing. All right, part 9, it says, which vector from exercise 8, which is the one we just did, would it make sense to call the opposite of V? That would be W. So to be opposite, you would be it would be multiplied by -1, right? So if you're ever asked to find the opposite, then you know you just got to change the signs. Part 10 says describe a rule that defines vector subtraction. So we're going to use the vectors v and u to support our reasoning. So if I take v minus u, let's do this mathematically. How would I do that? We would take 5 minus 6 and 7 minus 3 and produce -1 and 4. Perfect. So if we want it to produce a rule, you could say this is good for me, but this is the same thing as addition, just adding the other vectors opposite. They get technical here, but I think if you have this concept down, I think you're doing pretty good. Here's a good question. I don't know if that's the next question. It's not, because this concludes it. Would u minus v equal v minus u? No, they would not, right? Why is it? What do we know about subtraction? Not commutative. Very good. All right, that's actually all that I got today. I wanted to just go ahead and start lesson 18, but after reviewing lesson 18, I'm going to need the entire class period of uninterrupted mediation there. So go ahead. Oh, u minus v is not the same thing as v minus u because subtraction is not commutative. Yeah, so I'd said that these are not equal. The rule that they wanted you to come up with was like v plus the opposite of the vector. But in reality, as long as you understand that you're subtracting the first vector from the second vectors of their x's and their y's, then you got the concept down. Yes, that's fine. All right, with that being said, we are stopping. We still have